Hi again, everyone. Welcome back to our course in college algebra. In our most recent videos, we have been discussing the behavior of polynomial functions. And those are an important category of functions. And also, I note that you'll remember the class is really all about functions. And we have a class that's all about functions because functions help us describe the world. Now, different types of functions behave differently. We've had linear functions, absolute value functions, quadratic functions, polynomial functions. We're going to get into another type of function today called a rational function. So tell you what, I'm going to shrink down here. I'm going to get really tiny, and let's just get rid of that entirely. And I'll kind of scoot my way down here. Okay, so I am looking at a graph here on Desmos. Okay, this is the graph of y equals 1 over x minus a, and right now a equals 3. Okay, you'll notice this is very different from the graph of a polynomial function. Okay, for example, if I put in, something like this, y equals, just to make it kind of reasonable here, 1 over 10 times x minus 2 quantity squared times x plus 1. Oop, no, I don't want that up there. I want that down here. Okay, notice the polynomial graph, nice smooth curve. Okay, we have an x-intercept right there. Let me mute this for right now. We can see the graph is going to have an x-intercept at minus 1. It's going to have another x-intercept at 2. That's even multiplicity, so it's just going to touch the x-axis without crossing. Okay, so continuous smooth curve for our polynomial function. Whereas this, notice there's two disjointed pieces to this graph. It's not connected. You couldn't draw this without picking up your pencil. You could draw this part, then you have to pick up your pencil to draw this second part. And this is typical of what we will see in these rational functions. Now, when I say rational function, I'm talking about a function that is a fraction. It's got a polynomial upstairs and a polynomial downstairs. Okay, so it's a fraction with variables in the denominator, typically. Okay, so one thing that I want to think about is where this break happens and why this break happens in this video where we're introducing rational functions. So I want to change the value of a. So notice as I change the value of a, where that break is located, that switches. Okay, so let me do one more thing. I'm going to plot x equals a. And I want to make this, I got to go settings here. Let me go and make that a nice dotted line right there. Okay, so there's a vertical line at x equals a that this function cannot cross. So here when a equals 1, there's a vertical line at x equals 1 that the function cannot cross. Okay, at a equals 2, we got that vertical line that the function cannot cross. And that vertical line that the function cannot cross. Now that is called a vertical asymptote. Let me go over here to the document camera and examine something with you. So let's go to the USB camera. And we can maybe make that just a little bit wider. Okay. So we're going to examine the behavior of this function, f of x equals 1 over x minus 3 near x equals 3. And we'll make a quick note here. the domain of this function f of x is this set right here. It's negative infinity to 3 union with 3 to infinity. In other words, it's all real numbers except x equals 3. Okay, so this function has a value of x that is excluded from the domain. And the reason is this function involves division. And you cannot divide by 0. Division by 0 is undefined. And if I were to use x equals 3 in my function, I'm dividing by 0. So I can't do that. I am allowed to use anything else. In particular, I'm allowed to use anything close to 3. So let me look at what happens for various x values that get progressively closer to 3. Okay, so 3.1, that's kind of close to 3. All right, well, if I do the calculation here, 3.1 minus 3, of course that's 0.1, that's an easy thing to figure out. Then I have to take the reciprocal of 0.1, 1 over 0.1, that's 10. Okay? Let me try another one. 3.01, I'm going to plug that into the function. I actually get 100. Okay, so in fact you can just take a calculator, do a quick computation here, right? If I do 3.01 minus 3 equals, and then take the reciprocal, see that? 100, okay? If I do 3.001 as my input, this is even closer to 3. Let's look at what happens. If I took 3.001, I get 1,000. So what's happening here, this is increasing without bound as x approaches 3, okay? So in other words, I can make this output value as big as I want by choosing an x value that is sufficiently close to 3. Now let's switch back to Desmos here and see how we can pick that up in the graph. Look at this right here. The closer x gets to 3, right, the bigger the y coordinate gets. So we saw 3.1 comma 10. We're going to see that right up here. And the closer x gets to 3, the bigger the y coordinate gets. That's why the graph is rocketing up over there. And we could do a similar table and choose x values that are getting closer to 3 but are less than 3, and we would see we'd be getting negative values. In fact, let's go and check that out, right? Because this isn't the only way to get close to 3. That was getting closer and closer to 3 using x values that were bigger than 3. Let's use x values that are less than 3. 2.9 is kind of close to 3, but it's a little bit less, right? All right, well, let's do the computation, right? 2.9 minus 3 equals, take the reciprocal, and you get negative 10. If I do 2.99, which is even closer, we would get negative 100. If I did 2.999, we would get negative 1,000. Okay, so these numbers are all negative, and they're getting larger in the sense of absolute value the closer we get to 3. And once again, flipping back to the picture, we're seeing that right here. So as x approaches 3 on this side, the y values become more and more and more negative, and they plunge down. Okay, so this is typical of the behavior that we will see at a vertical asymptote. Okay, so let's go and kind of talk about some key features of rational functions over here. We'll summarize everything. Rational functions have vertical asymptotes. Okay? These are vertical lines that the function cannot cross. So as we saw in our picture just a second ago, this function has a vertical asymptote at x equals 3. Okay. If I change the denominator there, let's make it 1 over x minus 6, this function has a vertical asymptote at x equals 6. This function has a vertical asymptote at x equals 1. Okay? So you can probably make a reasonable guess as to what's going on. If you're looking for where the vertical asymptotes are for a rational function, you should look for values excluded from the domain. In other words, values that make the denominator 0. I want to flip back to the picture again. So we've got this function 1 over x minus 1. So we have this vertical asymptote right here, but we also have this kind of strange behavior over there. If we think back to our polynomial, notice as x gets large, y gets large. That's the end behavior of this polynomial, up to the right, down to the left. So as x gets bigger and bigger and bigger, y is getting bigger and bigger. But that is not the case in this rational function. As we go out here and get bigger and bigger x values, the y value is actually getting closer to 0. Okay, so this function has a couple of different behaviors that we haven't seen before. We have a vertical asymptote at x equals 1. Rational functions also tend to have horizontal asymptotes. Okay, so when we're dealing with these rational functions, which we will be for the next couple of videos, a couple of the key things that we'll be looking for is where are the vertical asymptotes, where are the horizontal asymptotes, and we'll put both of those things together and try and understand the behavior of these rational functions.